Yeah. So we'll start with the problem. Then we'll discuss. Yeah. Sorry. See, listen. We'll start with the problem. Then we'll go to the last concept. In 4.11, so there is a 100-turn closely wound circular coil of radius 10 centimeter that carries a current of 3.2 ampere. So radius is 10 centimeter, current is 3.2 ampere. So what is the field at the center of the coil? And the number of turns is 100. So what is the field? Magnetic field at the center is equal to mu naught Ni divided by R. Sorry, 2R. Mu naught is 4 pi into 10 power minus 7 into N is 100 into I is 3.2 divided by 2 into R is 10 into 10 power minus 2. So that will go 2 times. It is 6.4 into 10 power minus 5 divided by 10 into 10 power minus 2. So it is 0.64 into 10 power minus 3 Tesla. Oh, 6.4 pi, sorry. Okay, so 0.64 pi into 10 power minus 3 Tesla is the answer. Next is, what is the magnetic moment of this coil? So what is the formula for magnetic moment and magnetic dipole moment mean the same? So what is the answer? NIA, write it down. Sorry. So magnetic moment M is equal to N into I into A. The number of turns is 100, I is 3.2, and the area is pi r square. So 100 into 3.2 into 3.2 into, I'm approximating 3.14 to 3.2 into r square is 100 into 10 power minus 4. Yes. So it is 3.2 into 3.2 is how much? 30 is this 900. 1024. Huh? So 10.24 ampere meter square. Current into area ampere meter square. Okay. Next. The coil is placed in a vertical plane and is free to rotate about the horizontal axis. Where phi I am taking this. So they have given it, no? So the coil is placed in a vertical plane and is free to rotate about a field of 2 Tesla in the horizontal direction. Okay. The coil is placed in a vertical plane and is free to rotate about horizontal axis which coincides with its diameter. Okay. Coil and the coil revolving about an axis through its diameter, it is revolving like this. A uniform magnetic field of 2 Tesla in the horizontal direction exists. So the uniform magnetic field of 2 Tesla in the horizontal direction that exists such that initially the axis of the coil is in the direction of field. Initially the axis of the coil is in the direction of field. So when the coil is, so magnetic field is like this. If I take this to be the axis of the coil was like this. Okay. The coil starts rotating through an angle of 90 degrees under the influence of magnetic field. Now, if this kind of a scenario happens, initially what is the value of theta? It is 90 degrees. Because this will be the aerial vector. I told you clearly when you're trying to calculate the torque, NIBA sin theta, the theta refers to the angle between area and magnetic field. Is that clear? So when it is between area and magnetic field, then aerial vector is always perpendicular to the coil. Are you able to understand? Yes. Now, what are the magnitudes of the torque on the coil in the initial and the final position? So torque in the initial position is how much? NIBA sin theta. So N is how much? 100, I is 3.2, B is 2R. Area is or is what we can see. We need not sit. Yeah, right. MBA sin theta. No. This NIA is M. So you can write it as MB sin theta. M you have already calculated. What is the magnet? 10.24 into 2 into initial condition theta is equal to. Why did they take initially theta is equal to 0? What are the magnitudes of the torque of the coil in the No. We cannot take it like that. Let me read the question. The coil is placed in vertical plane. Okay. Axis of the coil is in the direction of field. Oh. Sorry. Yeah. So actually, the coil is like this, and its axis is like this. So there are two things here. I read the question wrongly. It is rotating about an instantaneous axis that is through the diameter, but the natural axis is horizontal. This is how it is. So initially, if you say this will be the direction of aerial vector, correct? So since the aerial vector is making an angle 0 degrees with respect to the magnetic field, initial torque will be still 0. Correct? Yes. But what will be the final torque? So MB sin 90 degree, which will be 20.48 into 1. That is 20.48 Newton meter. Correct? See, they have approximated it to 20. That's a different story. 20.48 would be a more accurate answer. Done? Now listen. What is the angular speed acquired by the coil when it has rotated through an angle of 90 degrees? So the torque that has been created when it has shifted from 0 degrees to 180 degrees is how much? I can take it as final minus initial. Let me, so that value is 20.48. Correct, 20.48 Newton meter. Let me call this as 1. But we know the fact that torque is equal to I alpha. Okay, but here you need to be careful with one thing, that you cannot take the final. I need to correct my statement. So there's actually a concept. So we know that torque is equal to mb sin theta, correct? So current is constant, area is constant. So magnetic dipole moment is constant, and uniform magnetic field B is a constant. But if you observe theta, theta is not a constant. So theta is equal to omega into t. So torque will be equal to mb into sine of omega t. But torque can also be written as I alpha. What is alpha? d omega by dt. So let me take this as 1, let this as 2. So mb sine omega t is equal to I into d omega by dt. Okay. So mb divided by I is equal to no need. D omega by dt. Or we can write it. No, that's what I'm checking. So what we can do is theta we can leave it as it is. Okay. Theta will leave it as it is. Here we cannot take time because they didn't mention anything about time. So even if I take time, there is going to be no use. So d omega by dt, can I write it as d omega by d theta into d theta by dt? So, but what is d theta by dt? That is omega. So mb sin theta is equal to I into d omega by d theta into omega. Accepted. So d theta I can take it to the other side. So I omega into d omega is equal to mb sin theta into d theta. Correct? Now integrate on both the sides. I into omega square by 2 will be equal to mb into minus cos theta from initially 0 degrees to finally 90 degrees. So when you substitute these values, I omega square by 2 will be equal to mb into cos 0, or it is only mb. So I omega, I in Radhinga, it's not current, it is moment of inertia. So I omega square by 2 is equal to mb. What did they ask? What is the angular speed upward, right? So omega final is what they're asking. So omega square I can write it as 2mb divided by I. Moment of inertia they have given a 0.1 kilogram meters per meter square. Sorry, into meter square. So 2 into 20.24 into b over 2 divided by 0.1. So 4 into 20.24 divided by 0.1. So if you calculate it, that's omega square it will give you. But we need omega, take the square root of it, that will give you the answer. Correct? Are you able to understand? Something like that. But I think they did a wrong calculation because 2 into what is m into b? M itself is 20, correct? M is 10 only. Then they did it right. 2 into 20 divided by 10 power minus 1 power half and quarter. That's fine. Correct one. So you get square root of 400. So try the next one. Example 4.12. A current carrying circular loop lies on a smooth horizontal plane. Can a uniform magnetic field be set up in such a manner that the loop turns around itself? A current carrying circular loop lies on a smooth horizontal plane. So there is a circular current carrying loop that is lying on a smooth horizontal plane. Can uniform magnetic field be applied so that it can be, the loop starts revolving? And that is the turns about the vertical axis. So they should be able to turn about the vertical axis. Is that possible? So it is lying. Can a uniform magnetic field be set up in such a manner that the loop turns around itself? If it has to revolve, we need to produce a non-zero torque. So think about it. So this is the direction of aerial vector. Okay, aerial vector. And you need to apply a magnetic field in such a way that is able to revolve like this. Then in which direction will you be able to generate torque? We know the fact that torque is equal to m vector cross b vector. So whenever you are doing the cross product between, say m vector, remember it is always either in the direction of aerial vector and the direction opposite to aerial vector. That's a known fact. So whenever you do a cross product between two vectors, we know that the resultant will be perpendicular to both the vectors for which you are doing the cross product. So if it has to revolve, you cannot generate it in the direction in which they are requested. It is not possible. Because the coil itself is, so the coil is like this, no? It should revolve on the horizontal. Like how you put dosa on a pan. Right? If this is a pan and they're expecting the coil itself to revolve in this, in the plane of the paper itself. This is not possible. Because when you apply torque, it will always be perpendicular to the plane across which you are trying to apply it. So you cannot generate a magnetic field. That is what they have mentioned. Second, a current carrying loop is located in a uniform external magnetic field. If the loop is free to turn, what is the orientation of the stable equilibrium? So stable equilibrium means what? Theta between whom? Yes. Theta between M and B should be 0. If it is unstable equilibrium, it should be 180 degrees. Okay. Unstable means it will first take a turn and then come back to its stable equilibrium position. Okay. No, in this case, it is not possible because it cannot revolve with the same plane. Yes. So this one, read the question carefully. There is a circular current carrying loop. Okay. Lying on a smooth horizontal plane. So there is a plane like this on which there is a circular coil placed. Okay. Can a uniform magnetic field be set up in such a manner that the loop turns around itself? Turns around itself means it should revolve above this axis. Okay, that's what I told, like how you put the dosa on the pan. Okay, so you put it on the pan, right? So if it has to revolve, in which direction will you apply the torque? So for that, you will say torque vector is equal to m vector cross b vector. Okay, so m vector is in this direction. Yes. Means you are saying the torque needs to be, so if it has to revolve about this axis, you need to produce a torque in the direction of aerial vector. Is it possible? Or in the direction opposite to aerial vector? Is it possible? No, because when cross product is taken, it is always perpendicular to it. That is it. Okay. B. So try to answer B, no? So read the question carefully and then you try to answer it. Sorry? The current carrying loop is located in uniform external magnetic field. The loop is free to turn. What is its orientation of stable equilibrium? Forget about flux. First answer the first part. So when will it be in the stable equilibrium condition? When it experiences zero torque. Because current carrying coil placed in external magnetic field by default will not experience force at all. So the only option it has is experiencing torque. So if you're able to make the torque also zero, you'll be able to generate a stable equilibrium. So torque என்ன சொல்றாங்க, it is mb sin theta. So to make it zero, when current is there and area is there, you can never make magnetic dipole moment zero. Magnetic field cannot be zero. So அப்ப theta மட்டும்தான் you can either make it as 0 degrees or 180 degrees. If you make it zero, it is stable equilibrium. If you make it 180, unstable equilibrium. So they have presented the same thing in a different way. They spoke about aerial vector and other things. Yes. In the case of an electric dipole and magnetic dipole, when you place a dipole in external uniform magnetic field, it experiences zero force, but it experiences a non-zero torque, depending on the orientation of it. It can still have a zero torque only in two situations, when is theta 0 or 180 over there. No, it is only a loop, because only a loop is a dipole. Current carrying conductor is not a dipole. A loop of irregular shape current carrying a current is located in an external magnetic field. If the wire is flexible, why does it change to a circular shape? So this also has something to do with flux. So let's not try to answer it. Done. So we'll see another concept, that is the application of torque experienced by current carrying loop. That is the moving coil galvanometer. So the moving coil galvanometer, if you see, it works on the principle of, so what is the principle on which it works? It works on the principle that a current carrying coil placed in external magnetic field experiences force. Current carrying coil placed in external magnetic field experiences force. Is that clear? Okay. So generally a galvanometer is also called as a moving coil galvanometer, or you can simply call it as MCG. Okay. So if you observe, when we say it is a device which works on the principle of torque experienced by current carrying coil, then how does the construction for it work? So how does the construction for it work? So first thing is you need magnetic field. So for you to generate a permanent magnetic field, what do you need? You need two permanent magnets. So if you observe these permanent magnets, they are in the shape of concave. So they have a concave shape associated with them. The reason for them to have a concave shape is they generate radial magnetic fields. So why do we have radial magnetic field? Is because this radial magnetic field will always be perpendicular to the aerial vector. Okay. When they're always perpendicular to aerial vector, what would be the torque produced by it? It is m into b, because sine theta will become 1. So the radial magnetic field has an advantage of creating the torque across the coil to be maximum. So that is the reason why we use a concave shape magnet and generate radial magnetic field. So this is an often asked question. Why is radial magnetic field important in galvanometer? What will you say? To produce maximum torque. Okay. Now, you have a coil which is wound around a soft iron core. Why we use a soft iron core? You will understand it based on certain magnetic properties of it in the next chapter. Okay. Because soft iron cores, generally what happens is they can get demagnetized easily. That is the reason why we use it. Okay. So there is a coil which is wound around it. Okay. And you are able to see this SP, right? You're able to see this SP. This SP is called as spring, or you can call it as hair spring. Why they are used is because when the coil starts revolving, the pointer is there, right? This will also start getting revolved. And to show us a particular reading, it has to stop at a point. But as soon as you remove the current, the coil is supposed to know that it should come back to its equilibrium position, that is 0. So to create that kind of a scenario, you need a restoring torque. And the restoring torque is created by a spring. Okay. Now, since you have a radial magnetic field, okay, when you have radial magnetic field, what is the torque experienced by this coil? It is NIBA sin 90 or NIDA. Correct? Now, what is going to be the restoring torque? So restoring torque is observed to be directly proportional to the amount of deflection that is created in the material. So torque will be equal to minus K into phi, where K is called as the torsional constant. What is it called as? Torsional constant, or some books refer to them as spring constant itself. Okay. Now, if you observe, the amount of restoring torque that is getting developed in the material is exactly equal to the amount of torque that we create by passing the current. Right? When that is a scenario, can I say NIBA is equal to K into phi in terms of magnitude. I don't want the minus sign there. So if I rearrange this equation, I'll get phi divided by I is equal to NBA divided by K, where this phi divided by I has a special name called as current sensitivity. So what is current sensitivity of a galvanometer? It is the amount of deflection that the galvanometer is able to generate when unit current is passed through it. Correct? The amount of deflection created in a galvanometer when unit current is passed through it. So this is phi divided by A, which is equal to NBA divided by K. So what is going to be the unit of it? So it is going to be division per ampere. Phi is just division. It is not flux. Phi is just division. So the division per unit ampere is what we call it as the unit of current sensitivity. Accepted? Now, if I take the reciprocal of it, then I'll be able to define I divided by phi. Then this I divided by phi can be called as K divided by NBA. Any idea about what this I by phi is called as? It's called as figure of merit. This is a very, very, very important parameter for a galvanometer. So it's called as figure of merit. Is it clear? Okay. So how is figure of merit defined as? It is defined as the ampere per division. So the amount of, so how do you understand it? To produce a unit deflection, how much current are we supposed to pass? So if the pointer is in this way, if it is 0 here, if it is 1 division here, exactly for the pointer to start from 0 and stop at 1 division, so to produce this much of deflection, how much current we need to pass is what figure of merit is all about. So this is, so two terms we have seen. One is current sensitivity and the second is the reciprocal of current sensitivity, which we call it as figure of merit. The next concept that we need to understand is voltage sensitivity. So what is voltage sensitivity? It is defined as phi divided by V. So this is equal to NBA divided by K into R, where R is the resistance of the coil of the galvanometer. So why did I write R there? Because V is equal to IR. NBA divided by K another. Phi by I. So phi by I, what should I multiply in the denominator? R. So NBA divided by KR is going to give us the voltage sensitivity, and its unit is division per volt. You will not say voltage, you will say division per volt. That's it. Okay. So these are all the concepts that are related to the galvanometer. Okay. So what are the three things we have seen? One is the torque that is being created is always maximum because of radial magnetic field. We have restoring torque. Mathematically, they both are the same. After that, current sensitivity, then we saw figure of merit, and then lastly we saw voltage sensitivity. Okay. So based on this, we will try out a problem. So two moving coil meters M1 and M2 have the following particulars. R1 is 10 ohm, N1 is 30. A1 is 3.6 into 10 power minus 3, B1 is 0.25, R2 is 14, and N2 is 42, A2 is 1.8 into 10 power minus 3, B2 is 0.50. Okay. The spring constants are identical for both the meters. Determine the ratio of current sensitivity and voltage sensitivity of M2 and M1. Do it. Correct. Yes. Current sensitivity 2 divided by current sensitivity 1 is equal to how much? Phi 2 divided by I2 divided by phi 1 divided by I1, or N2 B2 A2 divided by N1 B1 A1, because K1 and K2 will get cancelled. So correct. So voltage sensitivity 2 divided by voltage sensitivity 1 will be 1:1. Okay. Okay. The last two concepts that we can discuss now are how will you convert a galvanometer into an ammeter and a galvanometer into voltmeter. Suppose you have a galvanometer and it has a resistance associated with it. Let's call that resistance as capital, or we'll call it as RG, resistance of the galvanometer. Now, if you think of an ammeter, what is the functionality of it? It will measure the current. So if it has to measure the amount of current that is passed through it, then it needs to have less resistance or more resistance. It should have less resistance because to measure the complete value of current, it needs to allow all the current to pass through it. So if you are able to make that galvanometer into a device of lesser resistance, then you can make it a measuring device, and that measuring device is what is called as an ammeter. Okay, so how can you do that? For that, what you will do is take the resistance of the galvanometer. Okay, you take the galvanometer and you connect a shunt resistance. So shunt itself means parallel. If you connect a shunt resistor in parallel to the galvanometer's resistance, then this whole circuit put together will become an ammeter. Are you able to understand what I'm saying? Shunt in a parallel. Okay. Shunt in a parallel. So what you will do is the shunt resistance will be chosen with a lesser value so that the current is flowing through it. Okay. Dependent on if this whole combination, if it is called as an ammeter, let's say that ammeter is supposed to measure the value of current to be I. Now what will happen is the current will get split as IG and I minus IG. So why I said IG is because IG is the full scale deflection current. Means the current that you need to pass so that the galvanometer's pointer is at the end division that is available in that galvanometer. So I minus IG. Now what will happen is IG into RG is equal to I minus IG into RS. Accepted? Because The current through the galvanometer is passing through the resistance of the galvanometer. So the potential drop across the galvanometer will exactly be the same as the potential drop across the shunt resistor because they both are in parallel. So when that is the case, I can find what is the value of shunt resistance that I need to connect. Ig into Rg divided by I minus Ig. So if you know the value of current, the maximum current the ammeter is supposed to measure, then you can choose your shunt resistance in accordance with it. Are you able to understand? So the heading for that would have been conversion of a galvanometer into an ammeter. Okay. The next one is conversion of a galvanometer into a voltmeter. So how you do that? So generally, if you take an ideal voltmeter, this resistance is very, very high. It is supposed to be infinity. So you already have a galvanometer with resistance Rg. If you want to increase the resistance of that galvanometer, what I will supposed to do? Connect another resistor of high value in series with it. So that resistor, let us call it as capital R. So we need to find what should be the value of the capital R that I need to connect so that this voltmeter is V volts. How will I do that? So if you observe in this scenario, the current through the galvanometer is still Ig only. So wherever you see a galvanometer, the maximum current the galvanometer can allow to pass through it is Ig. So V is equal to Ig into resistance of galvanometer plus resistance, where V is the voltage that you want to measure. So V divided by Ig minus Rg is the value of the resistance that you can connect in series across the galvanometer to convert it to a voltmeter which can measure V volts. Okay. So this is all about conversion of a galvanometer into voltmeter and ammeter. Let's do this problem and we can wind up. Try out 4.13. In the circuit shown in the figure 4.27, the current is to be measured. What is the value of the current in the ammeter shown? Is a galvanometer with a resistance of 60 ohm. So in case number A, so if the galvanometer is of a 60 ohm resistor, what would be the current measured by it? I is equal to V by R. So V is 3 volt divided by R is 63. So it will be 1 divided by 21 ampere. So it will be 1 divided by 21 ampere. But now you convert it into an ammeter by shunt resistance of 0.02. Means to this galvanometer, if you are able to add 0.02, now what will be the resistance of this device in the first place? 60 into 0.02 divided by 60.02. R1, R2 by R1 plus R2. If you connect, yes. That's R1, R2 by R1 plus R2. You can directly find it. whatever resistance, that resistance should be added to 3. Then I will be equal to 3 divided by R equivalent. So R equivalent is 3.02. So you'll have 0.99 ampere. Are you able to understand? So in the third case, what are they asking? Had this ammeter been an ideal ammeter with zero resistance, if they mention ideal ammeter, by default it is with zero resistance, then what would be the value of current measured in this device? I will be equal to V by R. So that should have been 1 ampere. Yeah. In the third case, they are saying this ammeter is a ideal ammeter. Ideal ammeter, now what will happen in the third scenario? So ideal ammeter, now this resistance would have been 0. So if this is 0, this whole voltage will pass through this resistance. Correct? But it is an ideal one, right? Had it been an ideal ammeter, its resistance would have been 0. That is what they meant. Okay, had it been 0, then what would have been the current through this device? Okay, so that is all. Galvanometer. There is one concept left out, that is Ampere's circuitary law. Okay. So with this, I think we can wind up for today. Next class we'll see Ampere's circuitary law, and with that we are done.
Thank you, sir.
Okay.
Sir, when will we have the test?
I'll announce it.
Okay, sir.